All right, welcome everybody. My name is Maciej Mazurowski. I'm a faculty here at Duke. Welcome to the Duke Spark seminar, where we bring the leaders in the field of AI in medical imaging to talk about their work. A few words about our initiative. Duke Spark is an initiative for AI in medical imaging at Duke. We work on advancing the science and implementation of machine learning AI algorithms in medical imaging. You can see our website here, LinkedIn. Follow us on social media so you can learn about the events and our work. And I'm very happy to introduce Dr. James Duncan. He is Ebenezer K. Hunt Professor and Department Chair of Biomedical Engineering at Yale, and he's also a Professor of Radiology and Biomedical Imaging. Jim, thank you for being here, and please take it away.
Thank you very much, Maciej, and good afternoon, everyone, and it's a pleasure to be here. Let me just make sure my slides are up. Okay, so yes, today I'd like to talk about our work at Yale in neuroimage analysis in autism. And this has been going on for a number of years. So before machine and deep learning were a popular thing, I guess, so you can see a bit of our transition over time and how we've progressed, I hope. And this is a collaborative effort between our image processing and analysis group, especially Larry Stabe, Nisha Dvornik, and myself on the faculty. And my graduate student, Xiao Li, who actually finished her PhD, is now an assistant professor at University of British Columbia, and Juntang Zhuang, who's also graduated recently and is working out on in the West Coast at OpenAI, perhaps improving ChatGPT or something. We'll see. And all of us collaborating, especially with folks in our Child Study Center, particularly Pam Ventola, who is a child psychologist working with children in autism. So the autism spectrum of disorders are neurological developmental disorders characterized primarily by social interaction deficits, impairment in language and communication, and repetitive behaviors. But they have there's a variety of comorbidities, including anxiety disorders, hyperactivity, depression and mood problems, and a variety of other things. It's quite prevalent in the US. The last number I had, and this I was 1 in 45, I think that's increasing children in these younger age groups. And it's about 4 times more common in boys than girls. Overall, the causes are unknown, and therapists and psychologists, psychiatrists tend to treat symptoms. And so in a sense, our work is trying to help out with that, to provide ideas and tools, in particular from, as you'll see, task-based functional magnetic resonance imaging data to help guide treatment strategies, perhaps even predict possible outcomes, et cetera. So our earliest work in this area was in collaboration with Bob Schultz, who is at Yale Child Study and has now been at University of Pennsylvania for a while. And initially, Bob and our group, we were looking at anatomical MRI, and these were subjects who were scanned in our 1.5 Tesla magnets back in the early to mid 2000s. But Bob took us into thinking about going beyond structural differences in sort of classical image analysis and begin to look at functional magnetic resonance imaging with task-based imaging by looking at bold signal responses and activations in different regions in the brain. And he, along with his colleagues, developed or started to use this faces houses task, where so subjects were placed in the magnet, shown alternating 25 or 24 second or so patterns of faces and houses. and trying to bring out responses in different brain regions in reaction to this. So, and he had about 14 autism subjects, 14 controls. They were young male adults. And interestingly, the summary, or here's a sort of summary on top of a particular subject, but in response to these tasks for the typically developing or control young adult, both the fusiform face area lit up or showed significant activation in response essentially to the faces. And then this parahippocampal place area lit up in blue, presumably in response to the objects or the house objects. But for this subjects with autism, they tended to only respond in the parahippocampal place area, suggesting perhaps that they were not reacting to the emotional visualization or picture of the human form. And maybe just, at least the suggestion was that faces were just another object in a sense into their brains, that it was just vases and houses were all one integrated thing. So we published this work and moved on, and we were, Bob actually moved on, Bob Schultz, and Kevin Pelfrey came on board at Yale Child Study and was our new collaborator in the Child Study Center. Actually, Kevin himself moved on to University of Virginia after this, but we still collaborate with him. And around the same time, Archana Venkataraman came to our group as a postdoc. She had worked with Paulina Golland up at MIT on her PhD. And in this sort of mix in the early sort of 2012 range, now we had 3 Tesla magnets. And instead of looking at individual regions, Bob and others in our child psychology neuroscience colleagues were starting to sort of hypothesize that really changes in subnetwork processing was appropriate or important in trying to distinguish autism. So we tried to develop a strategy, again, on group data, and Archana was sort of the lead in this in her postdoc days, to try to locate these functional subnetworks by using a strategy we defined as community detection. And again, it was task-based fMRI. Now, the tasks kind of got a little more sophisticated, I guess you could say. They were now alternate 24-second patterns of this human-like dot light pattern form alternated with this scrambled light pattern. And the idea was to bring out, response to the emotional form of and social processing form of seeing the human, and contrast that with the scrambled light patterns. So Archana developed this strategy. We, as the field had been doing, we imposed a neuroanatomical atlas. You could use neurofunctional atlases, but chose this one. This Destrio atlas had about 150 regions. It was convenient because on this free surfer software. And the idea was then to basically look for connectivity using Pearson correlations. So each region in the atlas would be correlated with all other regions in terms of their time series signal in response to repeated offerings or visualizations of that light point pattern. And so 150 regions were correlated to 150 regions using Pearson correlations. And you had 2 correlation matrices for the different groups here. Again, group data, so looking at control subjects, correlations, and then autism subjects correlations. And what Archana was trying to set up was to try to estimate latent parameters that were related to what she called synchrony, real simple kind of synchrony or connectivity parameters in each region, trying to show, was that region, low, medium, or high, or just low and high in synchrony to all other regions in terms of its correlations. And was that region, let's call it identified by Fij, greater than or equal to the connectivity or the synchrony and i.e. connectivity to that same region in the other group, the ASD group. So trying to estimate these latent parameters F and F bar, synchrony, while simultaneously trying to group into one of a few hypothesized abnormal communities that might separate autism and control, or just a normal control subject or region in that case. So Archin has set it up as this maximum a posteriori-like problem, where a joint probability density was set up of the regions, the functional the synchrony levels in the different groups, the observed connectivity or correlation matrices given different hypothesized communities. And we used expectation maximization to solve this maximum a posteriori estimation problem and estimate these latent synchrony variables, F and F bar, as I said, and whether R belongs to one of just a few abnormal functional communities, and publish it in these venues. So again, just to remind you, these were the tasks shown, the alternating human form and scrambled light form. And we had 72 children with autism spectrum disorder. These were about 6 to 7-year-old children, and 43 age match controls. So back in our 2013-14 time processing range, group data, it took us, even with whatever GPU boards we had on our workstations around then, over 3 hours to run all this, a group analysis. And if you sort of displayed what was, and she found from these group data that two abnormal communities popped out. One that she called hyperactive or hypersynchronous, where there was increased connectivity in autism spectrum disorders, that these were where synchronous regions, synchrony was greater in the autism group than the control group, and hypoactive communities where there was reduced connectivity in ASD, F bar less than F. So if you look at the sort of the average brain and sort of smooth it out and divide it in half and look at first the inner two halves and then the outer two halves, these pink and blue hyperactive, hypoactive communities map like this. And for partly, I don't know if you could call it for fun, but trying to sort of prove that there was some relevant and interesting information, this NeuroSynth database is available in the literature. That was many, many papers mapped onto different functional tasks. And you could take your sort of map here by region and sort of correlate to these meta regions of which you know have certain functionality. And our hyperactive community mapped onto regions where there was visual perception and pattern recognition highlights, which is the strength in ASD. And the hypoactive community, where there's less reduced connectivity, seemed to relate to regions where there was social emotional processing, which is a known weakness in ASD. So, however, all this was, as I said, group data. And we really were looking to kind of help guide and understand information about individual subjects. So the next step, we now began our evolution of collaborations and students and postdocs working on it, the problem. And now Xiaoxiao Li came on board. She, as I said, graduated last year in her PhD work. And we were trying to set this up. We did set this up as a classification problem of ASD and control from task-based fMRI, again using region ROI analysis, but to try to get an individualized biomarker detection. This took us more fully into the deep learning era, I guess, of this work, and sort of around the late or the 2017-18 range. Our collaborators were Pam Ventola and Kevin Pelfrey from Child Study Center. And we went through an evolution of this work, sort of starting with regular multi-layer perceptron networks, then convolutional neural nets, but ended up with this graph neural net strategy with some of the publications here. This paper is actually published in Medical Image Analysis in late 2021. So the setup went like this, aimed towards individual analysis, as I said. We started off we wanted to, again, use these atlases that we reduced for this initial stuff to a Desikan-Kiliani atlas. Only 84 regions were needed, but really it was just for computational efficiency to get started. And we called each one of these regions of interest a node in a graph. So you could say a set of nodes V, where the nodes correspond to each of the ROIs in this 84 region of interest graph. Then on each node, we had deposited on it, if you will, a set of node features, and we used 100 features per node or per region, sort of hearkening back to the work I just showed you. But now we had a bold signal mean, a bold signal standard deviation, the Pearson correlation value of each region to all other regions, and some sense of an ROI coordinate. So now we had nodes and features on each node, about 100 of these features per node. And we also added edges to the graph, where the edges were now partial correlation. So correlation of a region to another region controlling for all other regions, sort of a sparsity-like calculation. And, we had similar data set size to what I talked about the last time. So we had to augment by resampling ultimately, as you'll see later. And here is the processing strategy. So we called it brain GNN, brain graph neural net. The earliest, as you'll see, step is more of a graph convolutional net, and then a multi-layer perceptron stage for pooling and node reduction. But the overall net, we called it brain GNN. And we started again with the task-based functional MRI data. Again, that same alternating light pattern of that human light pattern form and scrambled light form we call biopoint. Imposed the 84 ROI Desiccon Kiliani atlas on these 3D task fMRI data. Computed for each of the ROIs the mean time series and the standard deviations in there. Did the correlations, both the Pearson and partial correlations, to construct the graph. Pass that whole graph through our brain graph neural net processing, have a flattening or readout layer to get a classification, and now both really classified into ASD or control while inferring importance from the different regions and getting biomarkers, and simultaneously from the training data trying to group into communities or subnetworks, again, sort of mapping back to our earlier Bayesian work and trying to include that. We felt that the graph nets were, we tried different things, but these were computationally more efficient, and we thought a little more directly interpretable. And also they're scalable. They tend to be fairly effective, we thought, for classification, and as I said, pretty efficient. So here's the architecture in sort of a block form. Here's the graph neural net set up from the task fMRI data, and it was run through 2 graph convolutional processing stages, then with a multi-layer perceptron flattening and readout stage for the classification. By the way, I've neglected to say we could use the same architecture for regression. We tended to go in another direction, but we are going back looking at that. For the sake of explanation, all this initial work was for classification. Each one of these blue blocks then consisted of a green and a yellow block. The first one is a node convolutional layer, and this was to take, this is where the node features change. We start with 100 features on each node and try to reduce to an essential set of features, reducing in each stage. And then the second layer is, our second processing stage is a node pooling layer. And here the node features don't change, but the graph structure changes. We're trying to reduce to an essential or effective set of most important nodes. And all of these then could be aggregated into a vector. So let's look at each one of these green and yellow blocks to get a little more insight. So first, the green block we called an ROI aware graph convolutional layer, as you'll see. And let me set it up as follows. In a traditional graph convolutional net, usually you treat the nodes in the graph fairly identically, and you might apply the same kernel to all nodes. So Wi equals Wj. But when the nodes have spatial or functional relationship information, you might want to reduce to a more essential set of things. And so we did this, and we called it a ROI-aware graph convolutional net, where the ROIs, again, are the nodes. We start with and we hypothesize so many communities, again, kind of subnetworks from the literature or hearkening back, as I said, to our earlier work. And the kernel embedding then shows a representation via a particular basis set that depends on the number of subnetworks or communities you choose. And we start with a soft community assignment and end up with a conditional kernel embedding. And so the processing here, the embedding step is really fairly straightforward. Here's the features at each node. We'll find weights on each feature, and we'll add in this embedding, which is the surrounding nodes or all other nodes in a neighborhood on the graph. And we'll find weights there and edges that embed the whole the given node I into this framework of relations, and then come up with the H tilde, which is a reduced set of features. So this is an updated node feature vector due to interactions with other nodes weighted by Wj and Wi as well. And these can be, but however, we not only set it up like this, we had a graph convolutional net that solved for the H ins to get the H tilde outs. To a more effective set of features. But simultaneously, we had a multi-layer perceptron that was trying to learn a community membership from the training data only and projected it into this space where beta are the number of hypothesized basis functions and alpha are the weights of each region or membership in that basis function with some offset. So instead of finding the Wi's and Wj's, in a sense, simultaneously or in parallel in the training set, we hypothesize the basis vectors, find the best representations, and find the weightings for that. So alpha IU is a membership likelihood during training of the ROI I in community U, and beta U is the basis function for that. So all this goes on only really during training. So again, with our 72 ASD and 43 healthy control subjects, we hypothesize 8 communities. This is from a paper, actually from a sister lab at Yale, Todd Constable's group back in 2015. They wrote this functional connectome fingerprinting paper in Nature and sort of basically felt that 8 communities was a reasonable number to look at in different kinds of social processing and other tasks related to our work that we found appropriate. And we could map this out during training to say, here's the number of communities, here's the ROI value or membership, and we can assign community membership. And we got these sort of 8 communities. I don't really have anything to say here, except they're shown in color. It's out of the training data. It's roughly matches plausible things, but we're using it really as just we find these and then we use them from the training data as a lookup for later on. The second stage in our convolution, in our brain GNN network, is a salient ROI selection or pooling layer. This is the yellow layer in the slide I showed earlier. So now we have H tilde where the features have been reduced at the 2 processing stages from 100 to 16 and then to 8. But during the yellow processing stage, we now have a reduced number of features. And during learning by a loss function that I'll show in a second, we find a learnable projection vector that's in this sort of second stage, a pooling vector that's learned. And when we learn that, we take the feature scores and project them onto that vector implicitly and get a node score assignment, and then basically end up just keeping high scoring nodes to project onto the learned vector that's the vector most important for classification. So it's kind of a top K pooling. It's a variation on that. The real top K pooling has some issues. So we propose to learn pooling in an overall way using this global cost loss function for the entire graph convolutional brain GNN net. So where there's a classification loss is just set up as a cross entropy term between the training data. But then there's 2 other terms that are embedded with weights, a distance term that tries to make sure that it pushes away low pooling scores during training, and a group consistency loss, which you can dial in with lambda 2 during training, and either learn learnable vectors that are more or less individualized or more consistent with the group. So basically, we take all the data, learn all these multi-stage loss functions, and implicitly have this sort of projection and learned onto this community space, as well as do both a feature reduction and a node reduction. So here's some sort of just visual results. So again, this loss function, the global consistency loss, by the way, is just a matching of the vectors in that node to the average vector in the overall group. Here's 3 test subjects. The first one is when lambda 2 during training is essentially weighted 0, so there's no similarity term to the group. And if you look at these 3 subjects, this biomarker importance now is found by taking the test feature information at each of the nodes and projecting it onto the learned final training vector. And things that match well are given high importance, or more red, I think it is, and yellow less important. Oh no, yellow is most important, sorry. Red is a little less important, yellow more important. So this is sort of, all these subjects are run through classification, they're projected onto the vectors that are learned during training, and their importance scores are mapped out region by region for individual subjects. If we retrain it all and have lambda 2 weighted more for more similarity to the group, there's or 0.5 all the way up to here, it's the same 3 subjects during testing. And we found that this group consistency kind of tends to have a sort of a smoothing effect, which can be dialed in and is useful. So small lambda 2 during training gives less common important ROIs, and lambda 2 more common importance, more importance to the common information. So again, the biopoint task was used. The alternating 24-second over 6 repeats was in 3 subjects in a 3 Tesla magnet. Again, 72 autism spectrum children, 43 age-matched controls, fairly IQ matched for the neurotypical controls. And the classification results then went like this. This is more the only real quantitative result that we can have. But so we have 72 ASD or autism spectrum subjects. We augment them 30 times to get to about 2,100 subjects, 43 controls augmented 30 times to get to 1,200. So we end up with about 3,450 data sets. Divide these into 3 folds for training, 1 for validation and 1 for testing. And, you know, these kinds of 100 iterations, learning rate of 0.001, anneal to half every 20 epochs, basically had 690 graphs with augmentation per fold. So we compared across these classification parameters, accuracy, F1, recall, precision. And these are the number of parameters in these different comparison algorithms that were needed. So support vector machines, you can get a 62% accuracy of classification into autism or control using that strategy, and has a low number of training parameters. But and as you move through random forests, multi-layer perceptron, neural nets, a convolutional neural net, and different graph nets, early forms of our own, the classification gets a bit better. Our brain GNN did pretty well, almost 78%, with a medium number of 41,000 parameters to learn. The convolutional net has the most, and some of these have less, but we thought this was a reasonable compromise. And in this case, we used 0.1 for the weighting on the lambdas. So that's sort of the story of the graph convolutional nets, the brain GNN for classification. We can look back for each test subject and find these biomarkers, and then we can sort of relate those biomarkers to the communities learned from training to try to do some interpretation. So all of that interesting, but we really wanted to get into outcome prediction and relationship to outcomes from cognitive therapies. This would be our sort of ideal thing, so that we can help steer therapy, encourage parents whose kids come in for different kinds of therapies when they have autism. And so this is our collaborator, Pam, working with her daughter on one of these therapies known as pivotal response therapy. And that's the one we focused on in this initial work. And it targets social skills development. It tries to bring out emotional and social responses from the children with autism. It was developed by a husband-wife team back in the 70s at UC Santa Barbara. And however, it's pretty intense. It takes something like, I think it's 4 months of intense 6 hours a day, every day with the patients and families and therapists. And no one size fits all, you have to adapt it a little bit. And early intervention is crucial, yet treatment's really currently assigned quite randomly. And whether or not and no one knows if the child is going to respond or not. So the question we posed to our initial efforts in this direction was, can we predict treatment outcome from baseline measures, especially in particular task-based fMRI? So here was our setup with this. We again used so we imaged children all with autism now in a 3T magnet with alternating human-like forms and scrambled light pattern forms. And these are the acquisition parameters. They're about 3.5 cubic millimeter voxels, 4 millimeter voxels. And these coherent and scrambled point patterns were shown. And they were shown in alternating blocks of 24-second duration and repeated 6 times. In this and very early work, we only had 21 children, 14 male and 7 female. We are now up to about over 35 or so. We just got that grant renewed last year and had new subjects added. But this initial work had 21 children. Nisha Dvornik, my colleague, sort of spearheaded this work in our group. And mean age about 6 years, 5.8 years, 5.9 years. And these were highly functioning kids with autism, so, better performing to get the initial work done. We measured both at pre and post-treatment severity scores, especially related to this autism diagnostic observation schedule. And again, in this early prediction work, we focus on one of these, the social responsiveness scale score, was scored in this 0 to 1 or 0 to 100 range. Lower SRS meant better social function. But we were really looking at, could we predict treatment response, the percent change or the difference between post-treatment and pre-treatment, doing this pivotal response treatment therapy based on the pre-treatment baseline scans, with the idea that ultimately the predictive modeling might guide the treatment assessment. So here's our setup for this. So we went to, this is time varying, we went to looking at the information over time, the time series data, and went to invoke recurrent neural nets in a particular way, as you'll see, using long short-term memories. And so we had, again, a modest number of regions using this automated anatomical atlas, about 90 regions, looked at just the time series information acquired from the task-based acquisitions, but also, as you'll see, included phenotypic data. The learning algorithm then was this recurrent neural net with built on long short-term memory modules. Each LSTM, perhaps as some of you know, has 4 weights that need to be learned in here. In this design, a forget layer, a gate layer, input gate layer, an update of the current state, and an output layer. And so what we do is run this data through this, train it up, and try to predict a particular change in SRS score, given the output with certain treatment outcomes already known. Now, this is a small amount of data, so we really had to augment it heavily, I guess you could say. We parcellated things into 90 ROIs based on the biomarker analysis from before, sample the voxels in each ROI and replace them, compute the average time series. And we did the augmentation about 50 times. Here's the architecture in more detail. So now here's the task-based fMRI data. There are 24-second acquisitions repeated 6 times, sampled every other second. That gets you about 144 time points, and a few time points added at the beginning and the end. For each time point, 90 regions of information are taken as an input vector to an LSTM cell. So the 156 time points, 156 LSTM cells. Each LSTM node, or there are 8 LSTM nodes, I should say, per cell, and 4 sets of weights needed to be learned for each along short-term memory. We used, and the idea was to run this sequentially, learn the information, go through a fully connected node at the output, and learn the percent change in the SRS score. Since the sequence is aligned, we can do this sort of based on only the last time point. In addition, however, we wanted to incorporate the simple phenotypic information. We did it by using it to initialize the first hidden state and cell state of the first LSTM module in the sequence by connecting the phenotypic inputs to a dense layer representing the initial hidden state and the initial cell state, and these are passed along. So here's some of the results we have so far. Again, bootstrap, data augmentation, and subject-specific outcomes. We had the 21 subjects, so we used 20 subjects for training, 50 augmented data sets, noise added, as I said, so about 1,000 training subjects to test on the final subject. Then we will now cross-validation and rotate the test subject and do it again and again. Each input, remember, is 90 regions from the atlas with 156 time points per region. If you just use the data, no augmentation, we got some correlation effect of the predicted change in SRS score to the true outcome. So at least was somewhat of a hint of something. But if you do the augmentation, it got it up pretty good to 0.53. And interestingly, by initializing with these phenotypic variables, just age, sex, the full IQ, and the baseline SRS score, the correlation of the predicted outcome to the true outcome was up in the 0.77 range. And so obviously we got to add a lot more data to this, but these are promising. So from baseline task fMRI data, we have a hint of who might respond to this intense cognitive therapy and help therapists encourage parents, and ultimately, perhaps from longitudinal short acquisitions in the beginning, even steer the therapy. So we're, as I said, we actually just got this grant renewed last year. We're pretty happy about that these days with NIH funding. You never know, right? And so our next idea was to move this along from to combine the brain graph neural net ideas now on time windowed information from the task fMRI and send that into the recurrent neural net. This is the classifier version, but the predictor version, more similar to what I just showed you, is to then develop graphs at different time windows, do the brain graph neural net processing to the latent space of essential and important nodes, and use that parameter space to try to then predict outcomes, again, perhaps seeding with the non-imaging variables. And we've started this. My student, Jia Wang, has started into this, and we looked at dividing the time series into different sequences. This was a classification task. And we do see this kind of evolving biomarker importance over the time windows from these same data. So, and we could get classification accuracy up around 70%. So it's very, very initial work, but that's sort of where we're headed next. However, in parallel with all this, and a sort of an alternative strategy that I found quite interesting, that actually some of the methods got a bit of attention from the ICLR and NeurIPS communities, was championed by Junteng Zhuang, a student I mentioned who went to OpenAI. And it's a sense, it was parallel work to use, instead of functional connectivity, we went back to this work done by Carl Friston back in the early 2000s, known as dynamic causal modeling. And so, he looked for the effective connectome, the connections or the edges between nodes, if you will, in a brain graph. But he did it for only, the work in general was only for a few regions, and we wanted to move it up to whole brain dynamic causal modeling. And the real crux of this work is computational improvements to get us there. And Junteng developed what he called the multiple shooting adjoint method that was a series of papers to kind of speed up the way integrals were calculated, as well as gradients, as I'll sort of point to that. But back to the initial problem, we had, here's the brain. You might have certain regions with each region having time series information. We'll call those nodes. So just 3 nodes, for instance, would be Z1, Z2, and Z3 of T. There's an external stimulation. It'll be our task-based alternating human-like forms and scrambled light pattern forms. And we define the interactions among the nodes as D sub ij, the influence of node I on node J, and U of T, the external stimulus, if you will, the tasks of the human light pattern and the scrambled pattern on any brain state. In addition, we note that the external stimulation is set up to affect interaction amongst regions. So this is set up now as a model, as a differential equation problem. And the dynamic causal modeling says that the change in the fMRI signal at a node over time is dependent on the effective connectivity matrix times the time series information at each node, plus a weighting matrix times the external stimulus. And furthermore, you can model the change in the effective connectivity with time as dependent on this B matrix that you will find and learn from times the stimulus. So set up like this. So if there are P nodes, Z of T is a P-dimensional vector at each time T, D of T is a P by P matrix. And if there's K-type tasks, U of T is just, for us, just 2 tasks, scrambled in human light patterns, dimensional vector, 2-dimensional vector. C is a P by K constant matrix, and B is a P squared by K constant matrix. How much the external stimulus affects each ROI, how much it affects connectivity. So this is the guts of the algorithm, a little bit anyway, and realize that this is not neural nets. This is just solving numerical problems to solve for a parameter matrix. So U of T is the stimulation curve for our 2 tasks. We just have 1, 0 for the human form, 0, 1 for the scrambled light form pattern. For each subject, the method learns these embedded B, C, and D of 0 matrices. We'll group at time 0, we'll group them as eta, a parametric form. And it fits, we fit an ordinary differential equation with that function to the fMRI time series data. So we set it up as a parameter estimation problem. Z tilde are the measured time series, Z bar is the estimated one. We're trying to find the optimization or find the argument that minimizes those parameters such that those differential equations hold that I showed on the last page, these ones here. So the algorithm, just until convergence, after initializing B, C, and D of 0 with random variables, solve the ODE, get the estimate, compare the estimate, there should be a bar there with the measured Z tilde, calculate the loss, calculate the gradient, and then of the loss with respect to the parameters, then update the parameters. Basically run this till convergence and update B, C, and D0. And once it's all converged, we can read out an implicit result for Z bar at all nodes and D of T, the effective connectivity. Now, as I said, sort of the guts or the more details on our work are really these 2 papers by Duncan on using this a checkpoint adjoint method for the gradient calculation in the ODE, and optimizer that adapted the step sizes of the belief in the observed gradients. But the bottom line is, for one subject using a fairly standard, I think, GPU, we can fit B, C, and D0 and estimate D of T for all 116 ROIs in this other atlas we used in about 20 minutes. The previous dynamic causal modeling was much slower and limited to only 10 regions, so we feel this is enabling this for more global brain analysis. So for one brain, here's a result. Here's the whole brain effective connectivity. Again, we use an atlas with 116 ROIs, alternating tasks of the human form and the scrambled light pattern form. And while I don't expect you to sort of see too much, this is the effective connectivity evolving over time. And if you took out like the upper triangle here and the lower triangle and looked at them separately over here, you can now get some sense of what's connected to what. Red is a positive weight, blue a negative weight between nodes. The thickness of that is a strength. There's arrows in there hard to see of the directionality. Here's the lower triangle. And so while that can drive you crazy looking at that, there is sort of interesting pattern that you can derive from this dynamic causal modeling strategy, depending on the effective connectivities. So to get some feel for how this was doing, we ran it into a classifier. You could really put in any classifier here. We used this an invertible network that Duncan had developed, where the X1 and X2 for each layer are inputs and Y1, Y2 outputs, and F and G just a sequence of convolutional layers. But bottom line is that any classifier could be used here, perhaps neural net classifier. Take the connectivity matrix at each time point. We had 120 time points, and reshape to a 1D vector and run them through this and classify into ASD or control. This was a neural net in this case that we used. And we compared it to functional connectivity. So found using 116 by 116 Pearson correlation as the input at each one of 120 time points. And the effective connectivity was found using the strategy I just said, the dynamic causal modeling, and our multiple shooting adjoint approach for calculating it. At the output of the classifier at each time point, we get a fully functional connectivity or effective connectivity result. We get it for all 120 time points and use a majority vote out to plot something on this graph for these different classification measures. And we compared a vector into the classifier that was just Pearson functional connectivity in blue, just effective connectivity in orange, and then a concatenated vector of both functional and effective connectivity in green. So interesting that this is for 82 children with ASD and 48 age and IQ matched controls. We did 5 independent runs of a 10-fold stratified cross-validation. And the interesting to me anyway, and interesting to us in general, was that when you did the combined functional and effective connectivity, it did improve the classification numbers in some of these different metrics, especially recall and to some extent the accuracy in the F1 metrics. So we're encouraged by this. We're sort of thinking if this is a good way to go to keep including the effective connectivity. There is some interpretability in this. If you look at the as a biomarker, you can compute things per subject, but here's the sort of the group-wise interpretations that here's where there's effective connectivity connections where the ASD group has a stronger contrast than the control group with directionality. So it's plausible from sort of left thalamus to left inferior occipital lobe, right temporal pole to left inferior occipital lobe, kind of where the ASD group is stronger. But maybe more telling is where the ASD group has a weaker connection in blue with directionality. This relates to social processing. And so these directional things, again, fusiform, angular gyrus to fusiform. So somewhat interpretable, and we're encouraged by that and kind of working to continue this now. So that's it. Thanks for your attention. I think I tried to show some sort of an evolution in some promising both traditional and deep learning methods, especially graph convolutional nets for biomarker identification using task fMRI. I showed a machine learning strategy using recurrent networks that could be used for predicting response and move towards more personalized treatment. Our ongoing trends and efforts, and at least in our own work, are to continue to use data-driven networks, but now to try to bring in more complete spatial relations and time series information, perhaps in the direction of attention and things like spatiotemporal transformers. We can try to group or cluster into subnetworks and use that for interpretation. We're still looking to see if effective connectivity is a useful direction and might be for classification, biomarker extraction. And then we got a lot of next directions we're kind of trying to get there. There's a lot more resting state data around than task-based data in general. So can we do sort of use that in some kind of domain adaptation or transfer learning? we're using invertible architectures for certain things like classification. Again, context will be helpful, and obviously more interpretability and explainability. We also have a pretty good collaboration with our MR spectroscopy group. So we've looked on and off of incorporating, it's difficult in getting spatial distribution of this, but we are looking a bit at metabolic signals like GABA and glutamate, and see if those are useful in connection with the connectivity ideas. And always personalized and individual subject analysis is the key, and will be our focus going forward. So I want to acknowledge NIH, NINDS for this grant that's been going for over 20 years, actually. You know, we're encouraged, and we really enjoy this project and have some great collaborators. So thanks for your attention, and very happy to take questions.
Thank you, Jim. It's quite an impressive body of work, looks like over many years. I wanted to encourage everybody to ask your questions in the Q&A section. So just type your questions and I can read them. We have one, but I'm sure you have more questions. Let me get started, actually, as we're waiting for more questions. A general question to you: what do you think are the most important developments that are coming up in this space? So for neuroimaging in general, but also particularly with the application to autism in the upcoming years. And do you think it will be more on the side of machine learning or imaging technology?
Yeah, it's a good question. Well, I mean, there are sort of multiple communities focused on this almost, or at least they all interconnect a bit, but I would say there's sort of a more neuroscience driven strategies perhaps, and then maybe more, but certainly aware of computational work. And then there's the computational strategies looking back. I mean, the neuroscience community generally seems to be liking connectivity as the directions in general. A lot of it's resting state based work. There's big databases like Abide, and they, you know, they're working on that and trying to do more and more interpretation. I think in general for both, and yet these different kinds of graph approaches I see popping up, at least in the computational community. I think in both, you know, attention-based ideas are probably the one that's getting the most attention, no pun intended, and also there is some thinking now, certainly our own thinking and others, of bringing in context as best as possible. And so that might mean both spatial, temporal, longitudinal, and maybe even multimodality context. I was hinting at the end between task and task-based and resting state data. So, and I don't know, I feel that there's more work looking at both individual regions and kind of clustering into things into community or in the subnetworks, what have you.
Okay, thank you. We have a question from the audience here. How generalizable is the brain GNN model for same phenotype or to study other outcomes? Right.
So we will see. We're actually, the renewal is exactly aimed at these some of these directions anyway. So we're sort of trying to slowly move into this of not just children with autism, but now with comorbidities like especially anxiety and like mood and depression disorders. So another collaborator from Yale Child Study, Dennis Sokoldalski, has cohorts of kids with autism, but with anxiety and outcome measures measured and recorded and different cohorts with different anxieties. So we're looking to apply something very similar to that and see how it goes. But I think that in a sense, when you ask about generalizability, it's a good question, because it's like, can we I mean, we feel it's generalizable as you include more information in the training set, right? Whether a large mixture of data is generalizable or whether you've got to tune the training to specific cohorts, we don't yet know the answer to that. My hunch is that as you look at, if the training data and the test data are from the same kinds of cohorts, you'll probably be probably get better outcomes, but you'll always have the struggle of getting large numbers in that cohort. You'll always have much more training data if you cut across cohorts. So we want to see if the training across many kinds of ASD and control subjects will be, generalizable, I guess, for different things, and the outcomes, I guess that's where we're testing is in anxiety for starters. So we'll see. We don't know yet. We hope it'll be fairly generalizable.
All right. So again, last chance to ask a question here. Just please type it in the Q&A section. So let me read another one from the audience here. What is the effect of the baseline fluctuation components in the BOLD? These fluctuations can introduce spurious correlations between brain regions, leading to false positives in connectivity analysis.
Yes, absolutely true. And also we're augmenting things. So if we're augmenting on top of that and generating augmentations on top of the noise, that's going to be tricky. So, I mean, I guess I would say that there will be some of that. There'll be it'll cause problems in the results if it's pretty noisy data, and false positives for sure will be one part of the problem. I think that, I guess at the moment it's pretty manual. We're looking like in the prediction problem, we have only 30 data sets, so we can look pretty carefully at what's going on. How do the signals compare? Are we getting commonality across subjects, or are there spurious regions that we might even throw that out for the time being? As far as in general, can we sort of computationally detect problems? I guess that's partly why we went in these graph nets. We went from not just Pearson correlations, but looking at edges and using partial correlation information and features across correlations and the signal to try to get more robust information. And we do need to do, we started this a bit of test, retest, let's say for the same subject acquired a couple of times, and see what we get in the connectivity patterns and in the classification and biomarker stuff. So it's mostly a brute force experimentation to see what the effects will be. Perhaps our more complex, if you will, net of bringing in more than just Pearson correlation alone might be helpful there, we hope. Solving things different ways, including the dynamic causal modeling, might make, that's why we're looking at these different strategies to see how robust we are to problems like these.
All right. Yeah, thank you very much. Thank you, Jen, for a great presentation. Thank you to the audience for being here and for your questions. Check in with us, follow us to see about the next presentations. We have some very exciting presentations queued up. Yeah, thank you.